This enormous ship can weigh around 100,000 tons, yet somehow remains suspended on water instead of disappearing beneath the surface. To understand why this works, first imagine just how much material and machinery are packed inside a ship of this size. Inside are enormous amounts of steel, powerful machinery, fuel, cargo, equipment, and structural components, all contributing to the ship's total weight. And that creates the first apparent contradiction. Steel is much denser than water, so why doesn't an enormous steel ship sink? The important detail is that a ship isn't simply a giant mass of steel. It is a carefully shaped hollow structure containing enormous volumes of air. That hollow geometry dramatically increases the overall volume of the vessel without adding anything, close to the same amount of additional mass. When the hull enters water, its enormous volume pushes a corresponding amount of water away from the space it occupies. That displaced water matters because water has weight, and the weight of the displaced water creates an upward force on the ship. Engineers call this upward force buoyancy, and it is the fundamental reason an enormous ship can remain supported by the ocean. So the mystery isn't how steel manages to float. The real question is how engineers make water carry the ship's enormous weight. Let's simplify the problem completely and begin with something much easier to understand: a solid block of ordinary structural steel. The block contains a large amount of mass inside a relatively small volume, giving it an average density much greater than water. As gravity pulls the block downward, the water pushes upward, but the upward force isn't enough to support its total weight. Now imagine keeping exactly the same amount of steel, but reshaping it into a giant hollow shell instead. The steel hasn't become lighter, but the overall structure now occupies an enormous amount of additional space. When that enlarged structure enters the water, it can displace far more water than the compact steel block ever could. The more water the hull displaces, the greater the upward buoyant force generated against the submerged structure. Eventually, the upward force becomes large enough to balance the entire weight of the ship and everything carried inside it. This is why changing the shape of a material can completely change whether the final structure sinks, floats, or reaches equilibrium. And this simple relationship between mass, volume, and displaced water is the foundation upon which enormous ships are designed. The principle behind this behavior is ancient, but its engineering consequences still determine how modern ships are designed today. The key idea is remarkably straightforward. Submerged objects experience an upward force created by the surrounding water. Those upward forces exist because water pressure acts against the submerged surfaces of the hull from every direction. Because pressure increases with depth, the forces acting on the lower portions of the hull become greater than those near the surface. The horizontal pressure forces largely cancel one another, while the vertical pressure difference produces the net upward buoyant force. This is why the exact shape of the submerged hull matters so much to the ship's floating behavior. A deeper or wider hull can displace more water, but changing those dimensions also affects resistance, stability, strength, and operating efficiency. That means ship design is never simply about making the largest possible hollow container and putting it into the ocean. Engineers must balance the amount of water displaced against the forces created as the vessel moves through that water. So buoyancy gives the ship the ability to float, but the hull's design determines exactly how that floating system behaves. Now we can ask the question that makes the entire concept easier to visualize. Exactly how much water must this ship displace? The answer depends directly on the total weight of the vessel at that particular moment. If the entire ship weighs 100,000 tons, it must displace enough water whose combined weight is also 100,000 tons. That doesn't mean the ship occupies 100,000 tons of water. It means its displaced volume contains that much water by weight. As the ship becomes heavier, it simply sinks deeper until its larger submerged volume displaces enough additional water. This is why the waterline changes when a ship takes on cargo, fuel, ballast water, or other additional weight. The ship doesn't need an engine pushing it upward. The surrounding water naturally provides the required supporting force. In fact, the ship would still float if every engine, propeller, generator, and electrical system suddenly stopped working. That distinction is important because propulsion moves the ship through water, while buoyancy supports the ship against gravity. Once you understand that separation, the mystery becomes much clearer. The ocean is effectively carrying the ship through its displaced volume. But displacement alone doesn't explain everything, because engineers must carefully shape the hull to create enough volume without excessive resistance. The hull must contain enough underwater volume to displace the enormous amount of water required to support the ship's total mass. At the same time, the ship must move through water efficiently, because every unnecessary disturbance requires additional energy from its propulsion system. This creates a fundamental engineering compromise between displacement, drag, structural strength, stability, and the amount of cargo the vessel can carry. If engineers make the hull too narrow, they may lose valuable displacement volume and reduce the amount of weight the ship can safely carry. Make the hull excessively wide, however, and the increased wetted area can create additional resistance as the vessel moves through water. The hull also needs enough depth and structural volume to protect machinery, cargo, fuel, ballast systems, and other critical equipment. So the final hull shape is not arbitrary. It is the result of thousands of engineering decisions interacting with one another. Every curve, angle, depth, and width influences how much water the ship displaces and how efficiently it travels through that water. And most of the geometry responsible for keeping this massive vessel afloat is hidden from view beneath the ocean's surface. That boundary between air and water isn't just a visual line. It tells engineers exactly how deeply the ship is sitting. The vertical distance between the water surface and the bottom of the hull is known as the ship's draft. Draft changes naturally as the total mass of the vessel changes through loading, unloading, fuel consumption, and ballast adjustments. Add thousands of tons of cargo, and the ship becomes heavier, causing the hull to settle deeper into the surrounding water. As the hull settles lower, its submerged volume becomes larger, allowing it to displace additional water and generate more buoyant force. Eventually, the increased buoyant force becomes exactly large enough to balance the additional weight added by the cargo. This automatic adjustment is one of the most elegant aspects of floating structures. The water responds directly to the weight being carried. Remove cargo, and the opposite happens. the ship becomes lighter and rises until enough water has been displaced to match its new weight. The ship, therefore, does not have one permanent floating position. Its equilibrium changes continuously with its total mass. That simple relationship between weight and draft becomes critically important when engineers calculate how much cargo a ship can safely carry. Floating is only the first challenge. A ship carrying 100,000 tons must also remain stable when waves and wind push it sideways. The key to understanding stability begins with two locations inside the ship that engineers track very carefully. The first is the center of gravity, the point through which the combined weight of the entire vessel effectively acts downward. The second is the center of buoyancy, representing the effective location where the upward buoyant force acts through the submerged volume. When the ship is upright and balanced, these two forces act along the same vertical line through the vessel. Now imagine a large wave pushes the ship sideways, causing the entire vessel to rotate away from its upright position. Once the ship tilts, the shape of the underwater portion changes, meaning the center of buoyancy moves away from its original position. That movement separates the buoyant force from the downward weight force, creating a rotational moment that can restore the vessel. In a properly designed vessel, this restoring moment helps the ship recover from moderate rolling instead of continuing toward a dangerous angle. This means the shape of the underwater hull is doing more than creating buoyancy. It is also helping determine how the ship responds to disturbances. Ship stability becomes even more precise when engineers examine how the buoyancy point moves as the vessel heels through small angles. The geometry of that movement allows engineers to define another critical concept known as the metacenter. The relationship between the metacenter and center of gravity helps engineers determine whether the vessel will tend to return upright after being disturbed. If the center of gravity is sufficiently low relative to the metacenter, the vessel can possess a strong initial restoring tendency. This is one reason heavy machinery and other dense components are often positioned relatively low within large vessels. But stability cannot simply be maximized without considering cargo capacity, structural requirements, fuel location, and the ship's operating conditions. Engineers therefore design the entire mass distribution of the ship, not just its external shape, to achieve the required stability. That is why loading a ship is an engineering operation rather than simply filling every available space with as much cargo as possible. A poorly distributed load can change the center of gravity and alter how the ship reacts to waves, turns, and other external forces. So beneath the simple image of a ship floating lies an intricate balance between gravity, buoyancy, geometry, and mass distribution. A ship's mass distribution cannot always remain fixed because fuel is consumed and cargo is constantly loaded, moved, and unloaded. This is where ballast systems become extremely important because engineers can deliberately move large quantities of water inside the vessel. By filling or emptying specific tanks, engineers can change both the ship's total weight and the location of that weight. Imagine a vessel becoming unevenly loaded on one side. Ballast water can help compensate for that imbalance. Ballast can also compensate for changing fuel levels because consuming fuel gradually removes mass from specific locations within the ship. The The result is a vessel whose floating condition can be actively managed throughout a voyage rather than left entirely to chance. But ballast water is not simply dead weight. Its placement affects stability, draft, trim, and the stresses experienced by the hull. Too much weight in the wrong location can create problems just as easily as too little weight, making ballast management a careful calculation. The ship therefore carries an enormous adjustable mass of water, specifically so engineers can control how the vessel sits and behaves. And that adjustable internal mass is one of the reasons enormous ships can remain balanced, despite changing conditions throughout an entire voyage. Floating is not the only problem. The hull must also survive the enormous structural forces created by its own weight and cargo. A ship this large behaves in some ways like an enormous beam, floating on a constantly moving and uneven support. Its weight pushes downward through the structure, while the water pushes upward from below, creating complex bending forces along the hull. The situation becomes more demanding when the ship encounters waves that support different sections of the hull by different amounts. If the middle of the ship is supported differently from its ends, the entire hull can experience significant longitudinal bending. Engineers analyze these forces carefully because repeated bending cycles can create fatigue within large steel structures over long periods. This is why large vessels contain extensive networks of longitudinal and transverse structural members beneath the visible exterior. Together, these members distribute loads across the hull and prevent localized forces from overwhelming individual sections. The result is essentially a gigantic steel structure engineered to remain strong while carrying enormous loads through a constantly moving environment. So beneath the floating surface is another hidden engineering system, one designed to survive the ship's weight, cargo, waves, and constant flexing. Everything becomes more complicated once the ship leaves calm water and begins operating in the constantly changing conditions of the open ocean. A large vessel can simultaneously move upward, downward, forward, backward, sideways, and rotate around several different axes. Every one of these movements changes the shape of the submerged hull and therefore changes the distribution of buoyant forces. Yet the ship is continuously responding to those changes through the same basic relationship between weight, displacement, and buoyancy. The ocean effectively provides a constantly changing support surface, and the hull continuously adjusts its submerged position against it. The hull, therefore, has to remain strong enough to handle changing loads while stable enough to prevent excessive rolling and pitching. That combination of structural strength and dynamic stability is what allows ships to operate far beyond sheltered waters. The important point is that buoyancy is not a one-time event. It acts continuously as long as the vessel remains surrounded by water. Even as the ship rises on a wave and then falls into a trough, water continues redistributing itself around the changing submerged volume. The ocean may look chaotic from above, but beneath the surface, the physics governing the ship remain remarkably consistent. The floating system becomes far more complicated when seawater enters a part of the ship that was supposed to remain dry. The incoming water adds mass to the vessel, increasing its total weight and forcing the ship to displace additional water. But flooding can create a second problem, because it may change the ship's mass distribution and therefore its stability. This is why large ships are divided into carefully engineered watertight compartments separated by strong internal bulkheads. These bulkheads don't necessarily prevent every flooding event, but they can prevent water from immediately spreading throughout the entire vessel. Keeping separate sections dry preserves much of the ship's original buoyant volume, even when one area becomes flooded. However, enough flooding can still reduce the ship's freeboard, increase draft, and compromise its stability margins. The important lesson is that buoyancy and stability are related, but they are not exactly the same engineering problem. A vessel can retain substantial buoyant force while becoming dangerously unstable if flooding moves its mass distribution in the wrong direction. That is why ship designers think about the entire three-dimensional distribution of volume, mass, compartments, and forces, not simply whether the hull can float. At this point, it may seem that adding more volume should allow a ship to carry almost unlimited weight, but reality is far more restrictive. As the ship gets heavier, the hull sinks deeper, reducing the amount of freeboard remaining above the ocean surface. Freeboard provides valuable vertical margin against waves, spray, flooding, and other conditions encountered during real ocean operations. A heavily loaded vessel therefore has less vertical margin available when large waves pass around the hull. This is one reason ships operate within carefully defined loading limits rather than simply maximizing the number of containers placed aboard. Structural strength also imposes limits, because adding weight increases the forces carried by decks, frames, bulkheads, and the hull itself. The ship therefore has several different limits that must be satisfied simultaneously before a loading condition can be considered safe. Buoyancy may tell us whether the ship can float, but engineering determines whether it can float safely and reliably. That distinction explains why designing a ship is much more complicated than simply making its hull large enough to displace water. Every successful ship represents a carefully negotiated balance between what physics allows and what engineering can safely control. Now we can finally put all the pieces together and follow the complete chain of forces, keeping this enormous ship afloat. First, the ship's total mass is determined by its steel structure, machinery, fuel, cargo, ballast, equipment, and everything else aboard. That mass creates a downward gravitational force acting through the vessel's overall center of gravity. The hull then enters the water deeply enough to displace a volume of water whose weight matches that total mass. The surrounding water creates an upward buoyant force through the center of buoyancy within that displaced underwater volume. If the ship tilts, the submerged geometry changes, moving the center of buoyancy and potentially creating a restoring moment. Inside the hull, ballast systems can then adjust weight distribution to compensate for changing cargo, fuel, and operating conditions. Meanwhile, the structural framework spreads weight and wave-induced forces throughout the hull, instead of concentrating them in isolated sections. Every part of this system is connected, meaning a change in mass, geometry, loading, or water conditions can affect the entire vessel. What looks like a simple floating object is actually a continuously balanced mechanical system involving thousands of interacting physical forces. So after everything we've seen, how does a 100,000-ton ship actually remain above the ocean? The answer begins with something surprisingly simple. The ship's hollow hull occupies an enormous volume of space. That volume allows the vessel to displace an enormous quantity of water without requiring the entire structure to be solid steel. The weight of that displaced water generates the upward buoyant force required to balance the ship's enormous downward gravitational force. The hull's shape determines how that displaced volume behaves, while its internal structure allows the ship to survive the resulting loads. Its stability comes from carefully controlling the relationship between the center of gravity, center of buoyancy, and changing underwater geometry. Ballast systems then allow engineers to adjust mass distribution as cargo, fuel, water, and operating conditions change throughout the voyage. And watertight compartments provide additional protection by preserving as much usable buoyant volume as possible when individual sections become flooded. So the ship isn't floating because steel is somehow lighter than water. It is floating because engineers have made water carry the steel. 100,000 tons remain above the ocean because mass, volume, water, structure, and stability have been engineered into one extraordinary floating machine.